Okay, I'm going to talk about forces and Newton's laws for a few minutes. Um, remember we studied Newton's three laws. Okay, so the first law, objects at rest will remain at rest, and objects in motion will move at a constant velocity motion when there is no net force. Okay, and no net force means our object's forces are balanced. They're all offsetting each other. Um, so this is connected to Newton's second law, which I guess we'll get to that in a few minutes. But so net force is zero means that your forces are balanced. If this is not zero, that means they're unbalanced. That means you have a net force acting on your object. Okay. An object's resistance to changing its state of motion, that was inertia. Remember we said inertia is something that's connected to mass. So it's not really something that we measure or we have an equation for, but it's a property of an object. The larger the mass, the harder it is to change its motion, since mass is a measurement of inertia. So if you've got a big, huge, massive object, it's going to be harder to change its state of motion. When an object has no net force acting on it, this means that all the forces cancel each other. So this never means that there's no forces acting, okay? Because you've always got like force of gravity, for example. Right now, my pen is at rest here, but it's got a force of gravity pointing downwards, and it's got a normal force from the table pointing upwards, and they're balanced. Okay, so that means all the forces cancel each other. And actually, I just talked about that. An object is at rest on a table, so the net force is going to be zero. Those two forces, one downward, one upward, cancel each other out, and the object's going to stay at rest. My pen is going to stay at rest unless something happens to change its state of motion. If an object is accelerating downward, the downward force is going to be greater than the upward force. So whenever you are accelerating, your net force is going to be in the same direction as your acceleration. Net force causes a mass to accelerate, and this is Newton's second law, which we also write as F net equals mass times acceleration. Okay, so then we got a few problems with this. You push on a cart with 84 newtons of force, you cause an acceleration of 1.2. What is the cart's mass? So we can use this same equation and solve for mass. Okay, if we want mass, then we're going to divide both sides by acceleration. So mass equals F net divided by A, which equals 84 divided by 1.2. And I need my calculator. Hang on one second. Ta-da! Okay. Clear all this weird stuff that happened while it was in my bag. Okay, 84 divided by 1.2 gives me 70 kilograms. My mass is going to be in kilograms. Okay. All right, another one. An 18 kilogram object is accelerating east at 5 meters per second. What is the net force? Here, we'll use the same equation, and we can just multiply mass times acceleration. So we're going to have 18 times 5, and that is going to give me 90 newtons. Okay, a 50 kilogram object is on a table. It's being pushed east with 20 newtons of force, and then it's got 20 newtons of force to the west. What is its acceleration? So let's draw our object. Okay, it's on a table. Since it's on a horizontal surface, we know these forces in my y direction are balanced. I don't have to worry about those. So when I think about the net force acting on it, I'm going to have a 40 newtons in my east direction and a 20 newtons in my west. So this might be this might be an applied force, a push on this object, and then this might be friction. Remember, friction always is opposing your motion. So if I want my net force, which I need in order to get acceleration, because I'm going to use this, and I'm going to solve this for acceleration. So I need acceleration is F net over mass. They give us mass. Okay. My F net is my vector sum of my forces. So I've got one force going in a positive direction of 40 newtons. I've got another force opposite direction of that. So I'm going to do the same kind of vector math that we've been doing, when we did displacement type stuff. We do 40 minus 20. And then I can divide that by my mass of 50. And that's going to give me 20 divided by 50, which is something 0.4. So it's moving at 0.4 meters per second. So every second, this object is traveling 0.4 meters per second more because of these forces that are being applied to it. Okay, let's see what else we got. A few more questions. According to Newton's second law, as force increases on an object, acceleration increases because they're directly proportional. So if we look at this Newton's second law in this form, okay, we see that as force gets bigger, this acceleration number is going to get bigger. We also see that as an object's mass increases, the force needed increases. Okay, so this number gets bigger, okay, then this number's also got to get bigger because force and mass are trying to think how to say this exactly. Force and mass are going to be direct. Force, acceleration and mass are inverse. Like if your mass gets bigger, your acceleration is going to get smaller. But if you're trying to keep an object accelerating, like you're trying to keep this value, then if this gets bigger, this one's also going to have to get bigger. So increases, force and mass are directly proportional. This one relationship sums up how free fall works. And then this talks about how this reminds us that free fall, if you're falling, no matter what your mass is, you still have the same acceleration due to gravity acting on you. So that means this force is going to change depending on the mass value, but the acceleration due to gravity is still the same. So let's see. Mass and weight. So remember, weight is our force of gravity. Okay. Weight changes depending on where you are because weight is mass times your acceleration due to gravity. If you're on the moon, you're going to have a different weight. You're going to have a different force of gravity. Mass is something that always stays the same, though. Remember, mass is like a property of an object. Okay, a pineapple weighs 107 newtons. What is its mass? We can use this equation and do 107 equals m times 9.8 and solve for m. That means we're going to divide both sides by 9.8. And that gives me about 11 kilograms. So I'm just using my weight, my force of gravity equals mass times acceleration. Also, we can calculate what's the weight of this object, 465 kilograms. That's going to be 465 times 9.8. That's going to be a big number. 465 times 9.8 gives me 4557, and that's going to be in newtons. Remember, all forces are in newtons, no matter whether they're force of gravity, force of friction, applied force. And newtons, the units for newtons they go back to this. They're kilograms times meters per second per second. Newtons is just a shorter way of saying that. Okay. Just really quick, last few on forces. Force of friction for sliding objects is always going to be in the opposite direction of motion. Force of friction is always like opposing our motion. And so in equations, we're going to end up subtracting it from the applied force. And that's like what we did in this example on the previous page, where we did 40 minus 20. Okay. According to Newton's third law, for every action force, there's a reaction force that is an equal value and an opposite direction. Remember, that's the one where like the ball bounces against the wall and they each have an equal force, opposite reaction. So gravity pulls down on you. The reaction force to this is that you actually pull on the earth. Okay. The earth doesn't feel that because it's so huge, but as earth pulls on you, you pull on the earth. You push down on the ground. The reaction force to this is the ground pushing up on you. Okay, so if I'm pushing down on this table, the table is actually pushing back up on me with an equal value opposite direction force. Okay, circular motion will be next.